This is part 7 of the series Circumference and Area, and in this part we're going to finish up our discussion on area of composite figures, and we're going to look at one final example here that's a fairly complicated example. So let's get started on this, and it says a manufacturer found a piece of blue anodized steel from which several geometric shapes had been cut. Two congruent tangent circles of radius 3 had been cut so that each circle was tangent to a side of the original piece of steel, and one line perpendicular to the sides of the original piece of steel could be drawn through all the points of tangency of the circle and their centers. Wow, that's quite the statement. A third circle that was tangent to three sides of the original piece of steel and also tangent to the two smaller circles was cut. Finally, an equilateral triangle that was tangent to the two congruent circles was cut. What is the total area of the pieces cut from the original piece of steel? So quite a complex statement here. Let's see if we can't break it down and determine what information is pertinent and will help us solve the problem, what information is superfluous and therefore can be discarded. So here, the blue anodized steel, we don't care what it's made of because we're looking for the area of shapes. So whether plastic, rubber, or steel, doesn't matter. We have two congruent tangent circles of radius 3. So we know that these two circles are congruent circles, which means their radii are the same, and they're tangent to each other, meaning this point is a point of tangency of both of these circles. It also tells us that the radii of these circles is 3 inches, and they've been cut in such a way that each circle was tangent to a side of the piece of steel. So in other words, this is a point of tangency, and this is a point of tangency. And it also tells us that you could draw one line that would be perpendicular to these sides that goes through all the points of tangency and goes through the centers of the circle. So that tells us that these circles are directly on top of each other, one over the top of the other. And that's a pretty critical piece of information to find the other values here. So we know that this radius is 3, this radius is 3, and there's a line that can be drawn straight through all of these so that we have a diameter and a diameter going through the points of tangency on both of those circles. All right, let's take this information and see if we can't start solving the problem. Well, the first thing I'm going to do is I'm going to try and eyeball a line through here just to see if we can't figure out where that is. So that looks about right. And if we guess properly, it looks like this would be a center. We're just eyeballing. It doesn't have to be precise because we're just sketching in things here. So that means this is 3, this is 3, this is 3, and this is 3. That means this side length is going to be 3 plus 3 plus 3 plus 3, which is going to be 12. So we know this side length is 12, which is a good thing. And then we know that the diameter of this circle is also going to be 12 because it's tangent here and here. So I guess the first part we can do is start off with the area of this guy. So let's call this, let's call this circle A. Let's call this circle B, circle C, and then this will be our triangle. We'll call that T. All right. So now down here we'll do the area of circle A. So the area of A is, the area is pi r squared, so it's pi r squared, which is pi. The radius, well, the radius of this circle is the diameter of one of these. So this is going to be 6 squared. which is 36 pi. We're just going to leave that like that for now because we're going to be combining these two later on. So now the area of B is pi 3 squared, and so that gives us 9 pi, and the area of C is exactly the same, so the area of C is 9 pi, so we're going to leave those alone. And then we need the area of this triangle. Now that triangle is going to be a little bit more difficult, I think, but not too terribly bad. We know that this altitude, I'm going to have to corrupt my drawing here a little bit. So we're going to draw the altitude in there, and that altitude breaks up the side length. So this piece is 6, and we know this piece is 12. That piece isn't going to really be relevant because area is going to be 1/2 base times height. I could use a height here, but there's no point in making things look really ugly. So this side length is 6, and I need to find this side length. So we can use Pythagorean theorem, or we could use our 30, 60, 90 relationships. So we can assume that we know the 30, 60, 90s, and if this is a 60-degree angle because it's equilateral, we know that this is 60 degrees, so therefore this is 30 degrees, and therefore this is A, this is 2A, so this is A square roots of 3, so this is 6 square roots of 3. So now I have that side length, so the area of T is 1/2 base, well the base is 12, times the height, which is 6 square roots of 3. Now to actually calculate the total composite area, we know the area of our composite is going to be the area of A, 36 pi, plus area of B plus area of C, which is 2 times area of C. So it's 2, or 2 times area of B, either way. 2 times 9 pi, plus this guy, area of T, which is 1/2 12 times 6 square roots of 3. Now we're going to go ahead and put this into our calculator, and we're going to get approximately 232 rounded to the nearest decimal. All right, well, it wasn't terribly bad once we broke down the description here. So let's move on to the next topic. In this section, we're going to look at the effects of changing dimension on the calculation of perimeter and area for a couple of different types of shapes. So here we have a right triangle. It has one leg given us as 5, the other leg as 12. And we want to determine what is the effect of changing one dimension. We're changing from this picture to this picture. We're changing one dimension. We're changing this dimension and doubling it. And what is the effect on perimeter and area of these two? So the first thing is we need to calculate the perimeter of this shape. Perimeter is just side 1 plus side 2 plus side 3. Here, luckily, this is a Pythagorean triple. So this is a 5, 12, 13 right triangle, or you could just use Pythagorean theorem to find it. But this is a 5, 12, 13. So let's make this side 13. And so our perimeter is going to be 5 plus 12 plus 13, which is going to be equal to 30. Now let's find the area. The area is 1/2 base times height. So this is 1/2 5 times 12. 1/2 12 is 6. 6 times 5 is 30. Interesting. The area and perimeter both are the same. Now I want to find out what happens to perimeter when we change this. So what we're going to have to do for perimeter, because we're adding the values, we can't do any kind of factor type change here because we're just adding three different numbers. And this number is going to be the same, but this one's going to be multiplied by 2, and this one is going to be dependent on these other two. So there's really no particular formula we could do. We're just going to have to take the 12 plus the 10 and find that guy. Well, fortunately, here we can use Pythagorean theorem. So let's call this C here. So C squared equals 12 squared plus 10 squared. Take the square root of both sides. This is C equals square root 144 plus 100, 244, which is approximately 15.6. So our new perimeter then, we'll call it P prime, is 10 plus 12 plus 15.6, which gives us 37.6. So what we would say then is our perimeter increased by 7.6 units. So we would say perimeter increased 7.6 units, whatever the units happen to be. All right, now let's see what happens with area. For area, it's 1/2 base times height. And we took the base and multiplied it by 2. So this is 1/2 2b times the height. Let's pull out that 2 and see what that did to us. 2 times 1/2 base times height. So what should be the outcome is our new area should be twice the original area, because we multiplied the original base, the 5, by 2 to get that base. So our real answer should be 60. Let's see if that's the case. We have 1/2 10 times 12, which is 5 times 12, which is in fact 60. So you can find out what happened to area simply by using a factoring process here. And so we would say area increased by a factor of 2. And now let's look at what happens when we change both pieces. So here, our new perimeter, we're going to have to find our hypotenuse. So this C is going to be the square root of 18 squared plus 10 squared, which is going to be approximately 20.6. So our new perimeter, we'll call that P double prime, is 10 plus 18 plus 20.6, which is 48.6. And we would say perimeter increased by 18.6 units. Now let's take a look at area. Well, this side is 5 times 2, and this side is 12 times 3/2. So we took area is 1/2 base times height. We took the base and we multiplied it by 2. And we took the height and multiplied it by 3/2. If we pull out the 2 and the 3/2, we get 2 times 3/2 times base times height divided by 2. So we multiply these together. 2 divided by 2 goes away. So the result should be 3 times 1/2 base times height. So we should say our area increased by a factor of 3. So 1/2 10 times 18, which is 90. And yes, in fact, 90 is 3 times the area here. And we would say area increased by a factor of 3. Well, that wraps up this series, and I hope to talk to you in the next series.